the basics of nuclear magnetic resonance, which is NMR. So NMR is a technique used to illustrate the chemical structure of a compound. Any chemical compound or any new drug molecules that has been newly isolated or newly synthesized. So NMR spectra comes from an atomic nucleus that has unpaired electron. So that can be a hydrogen nucleus or can be a carbon-13 nucleus. So hydrogen nucleus and carbon-13 are present in almost all biological molecules. Therefore, NMR can be used to illustrate the structure of those compounds isolated from the plants. Example, secondary metabolites. So one of the requirements for the taking the NMR spectrum is the compound is required in very pure form, so that we'll get the proper clear spectrum from that particular molecules. So next I'm going to the basic setup of the NMR instrument. So the NMR instrument can have a sample holder where you can put the sample, and it has a radio frequency transmitter which will supply the radio frequency to the sample, and there is a radio frequency detector which detect the radio frequency which is coming out of the sample, and there is a magnetic field which is supplied to the sample. So the entire setup is inside a nitrogen jacket and also a helium jacket. So it is kept in very cold conditions so that a very high magnetic field can be achieved. So the sample will be spinning inside the sample NMR instrument. So next I'm going to explain the basic principle of the NMR from the hydrogen nuclei. So this is a image or a diagram of a hydrogen nuclei where the hydrogen nucleus is surrounded by an electron, an unpaired electron. So there will be, when an electron is surrounding a nuclei, there will be a net magnetic momentum on the hydrogen nucleus. So I can show the animation. So when the electron is surrounding the hydrogen nucleus, there will be net magnetic momentum on the hydrogen nucleus. So when this hydrogen nucleus is placed inside a high magnetic field, the magnetic momentum of the hydrogen nucleus uh, will try to tilt and show a motion called precession. So a precession motion is just like a spin top motion. So where it is slightly slided to slightly shown in an angle, and it will move around that. This kind of motion is called precession motion. So the net magnetic momentum of hydrogen nucleus will show a little bit tilting when it is under an external magnetic field. The magnetic momentum of hydrogen nucleus is trying to oppose the magnetic field, external magnetic. So this kind of motion is called precession motion, where the net magnetic momentum of the hydrogen nucleus will be tilted and it will be rotating. This is called precession. So when you apply a particular radio frequency to the nucleus under precession, it will absorb a particular radio frequency and take a 180-degree turn. So the net magnetic momentum of the hydrogen nucleus will take a 180-degree turn, absorbing a particular radio frequency. And when we stop the application of radio frequency, the net magnetic moment of the hydrogen nucleus will come back to its original position, releasing a particular radio frequency. So this radio frequency will be recorded in the function of time, typing based using the structure of methanol. So here I am showing a methanol. The carbon is shown in black and the proton is shown in blue and oxygen is shown in red color. So this particular methanol is kept inside the NMR at a very high magnetic field. So the protons are showing position. So when we applied a particular radio frequency, it will take a magnetic momentum on the proton will take a 180-degree turn, depending upon the chemical environment. We are absorbing a particular radiation, taking 180 turn. But when we stop this radio frequency, it will absorb a particular radiation and come back to its or try to come back to its original position. So when they are coming back to its original position, they will release a particular radio frequency. So this radio frequency is recorded in the function of the time. And as it is shown here, those carbon which is those proton which is attached to carbon are called highly shielded, and which is attached to the oxygen is called highly deshielded. because the oxygen will drag the electron towards it because it is highly electronegative, and the net magnetic momentum on the hydrogens is very less. Therefore, it absorbs very less frequency compared to the proton present on the carbon. Therefore, they appear on the different position. Therefore, the kind of radio frequency emitted is different from each photon, depending upon the environment. So, when we receive all the signals from different kind of photon, we will get a resultant wave, a combination of all the waves. So, this combination of all the waves will be in the function of the time. So, we will be converting those waves from the function of time into the function of the frequency using Fourier transformation. So different spectrum recorded in the function of time will be converted into function of frequency using Fourier transformation method. So below is a Fourier transformed spectrum, NMR spectrum, showing the spectrum of a methanol molecules. So H hydrogen molecules, which is hydrogen atom, which is shown in red color, is highly de-shielded because it is present closer to the oxygen, and it will appear first, and those highly shielded protons which is attached to carbon will appear later, and both of the all the spectrum will be recorded in the reference compound called tetramethylserine, which is added with all other compounds. This is to avoid the variation between the NMR instruments. So all the frequency spectrum red will be related to the spectrum of tetramethylserine, so that the uniformity is maintained in all the instruments. So that's the principle of NMR. Thank you.